The shape of what we build, live, work, study, operate on, whether it be on the Earth, the Moon, Mars, wherever we're going, matters. Knowing that at a scale where we can understand what's going to happen, what has happened, and predict what could happen is really important. Laser altimetry, as developed here at Goddard, went from an idea to try to capture that into something we can actually do.
In 2018, NASA launched 2 next-gen LiDAR missions specifically to look closely at our changing planet. But if over 3 decades of LiDAR missions taught us anything, it's that laser altimetry at Goddard is an evolution of technology, propelled by scientific curiosity in the face of almost certain setbacks. Take the story of the tree-measuring LiDAR, the Global Ecosystem Dynamics Investigation, or GEDI.
GEDI had its genesis really in all the innovative work that had been done with LiDAR at Goddard. Some of those innovators, this was Jack Bufton and Blair at Goddard. Bryan had an instrument called Slicer that was flying around taking these cool LiDAR transects. And then they put an instrument up in space, the shuttle laser altimeter, and I saw some of that data. I thought, wow, this is really cool. We've never been able to look at canopies in 3 dimensions like this. There's certainly got to be some applications to this.
The shuttle laser altimeter was the first real test for LiDAR and provided the momentum for MOLA to take on Mars. But it also gave us a glimpse at what LiDAR could measure on our own planet. And so the push for the Vegetation Canopy LiDAR, or VCL, began.
It was a really innovative mission. We were trying to do something that hadn't been done before, but we were optimizing it for vegetation. Vegetation is very different than if you're looking at ice, or if you're looking at Mars, or if you're looking at the moon, because you have to have enough laser power to get through the canopy and get a strong return underneath the ground.
The VCL team could build lasers strong enough, but they couldn't get them to last very long. And that proved too risky for a very cautious NASA in the 90s.
After that happened, we focused on the Airborne LiDAR program. And this is again with Bryan Blair using a really innovative instrument he had called LVIS, the Land Vegetation and Ice Sensors, I believe it's called.
If you really want to get down to really high resolution and looking at the sort of landscape scale changes over the Earth, you need a swath mapping system. So sort of in the mid-90s, we started working on LVIS, and we really worked on that in large part because people said it couldn't be done, and it's really kind of drove us to see how much we could get out of that system.
Airborne missions were successful at keeping that momentum going, especially in the long periods between satellite launches.
Sort of a core of us kept going year after year, going from one instrument opportunity to another, and sort of making opportunities if we didn't have any. The thread that kept us all going was the airborne system.
Airborne LiDAR really plays a role at helping us understand how things work in real world settings.
Yeah, it's definitely the best way to go, is to build the hardware, get some data over real terrain, and actually show that it meets the requirements, that you can scale it to space.
But along the way also, as we were collecting those data sets, we were releasing those publicly and letting people experiment with them and get comfortable with them.
Dubayah, Blair, and others leveraged the success of LVIS to propose a new satellite mission, Destiny, a combined radar and LiDAR mission that could see through clouds down to tree canopies. However, NASA budget cuts sidelined a couple of Earth science missions, and Destiny was grounded indefinitely.
And that was a devastating blow, because we'd now been trying from 1995, and now it's 2010. We've been trying to get a LiDAR that was meant just for vegetation structure into space, using the best people in the world who are at NASA Goddard to do this. And at that point, I've been doing this 15 years, maybe I'll just quit. But of course, we really didn't quit. So we said, well, let's look for another opportunity.
That opportunity was on board the International Space Station with the GEDI instrument. GEDI wasn't just another successful LiDAR. It was the end of a very long road, hard fought by scientists and engineers dedicated to pushing the limits of what LiDAR could do.
We've been really pretty happy about the success of GEDI thus far. GEDI, again, is the first LiDAR that's been in space that was optimized to measure vegetation structure. And it's created an enormous amount of data. We've conservatively done about 10 billion estimates about getting those tree heights and getting that canopy structure.
But ultimately, we really wanted to get at the carbon content. What role do forests play in the carbon cycle?
GEDI has been steadily gathering data, chipping away at the global question of just how much carbon dioxide trees take out of the atmosphere, a big piece of the climate puzzle. The current LiDAR missions are all about building on the past.
Things that we, in fact, have only just begun to think about from pictures, now we have the third dimension.
ICESat will add the third dimension.
ICESat-2 adds the third dimension, the elevation.
Pushing the technology to get at deeper science questions. And so came the next generation of ice-focused laser altimeters, aptly named ICESat-2. Its single instrument, ATLAS, was designed to precisely measure small changes in the shrinking icy poles of Earth. To get down to that level of accuracy from space, everything had to be much better.
It's this story of these incremental improvements through time, and with each mission you're leveraging the lessons of the last mission. It wasn't a short process for ICESat-2, even though we knew a lot and had learned a lot over the last 20 or 30 years. Each mission, has its own challenges. All of the easy missions are done, as they say.
The first iteration of the instrument was going to be very similar to glass. As it turned out, the group that wanted the more complicated instrument won. So then they came back and said, okay, instead of digitizing a 40 hertz or 50 hertz laser or whatever, we're going to fire this beam to the ground and then individually time tag each photon that comes back.
There were so many requirements, there were so many constraints. We had constraints on the software capability, we had constraints on the storage space, we had constraints on the memory.
By photon tagging, they had built the detector system and the detector electronics. They were just, it was like a fire hose of data coming into us.
ATLAS has 6 beams, and it records elevations for each of those 6 beams 10,000 times a second, as long as there is reasonably clear skies that the laser light can go from the spacecraft to the ground and back again.
The Earth is much more complicated to work with because of the clouds. The algorithm could easily be confused and start following, the cloud surface. I was the lead for the receiver algorithms team. The responsibility of making this work fell on my shoulders. I had sleepless nights, I have to tell you, thinking that I wasn't going to be able to make this work.
In order to maximize the return from these data, a key component was determining the location on Earth of the laser bounce point, a process called geolocation.
So what we do in geolocation, we get the position of the satellite really accurately, we get the pointing of the laser beam very accurately, and then we have the range from the altimeter, and we add all those together to give us where that bounce point came from. Without the geolocation, you have lots and lots of error, and you wouldn't be able to measure the change in the height of the ice sheets.
We overcame what I think was fairly insurmountable problems, but everybody took their own piece of the puzzle and everybody worked it.
ICESat-2 launched in 2018, and months later began gathering data that shed new light on how fast the ice sheets are changing, how thick the sea ice cover was in the Arctic, and even measured beneath the surface of the water, up to 30 meters, a kind of bonus science result for a team that worked tirelessly to push the limits of the ATLAS instrument.
So you cannot just build just one LiDAR. You need a sustained team who's been building LiDAR for some time.